Hello everyone, this is the first part of our lecture Geoelectrics, Geophysical Sounding with Electricity. Geoelectrical methods were pioneered by the brothers Conrad and Marcel Schlumberger in the early 20th century. So they both have a German written name but with a French pronunciation because they are coming from Alsace-Lorraine. And Conrad Schlumberger was at the time a professor at École des Mines de Paris when he started to develop ideas about geoelectrical sounding. And after a lot of testing, so he developed the theory and experiments. The funny thing is that he did some of the experiments in his bathtub by filling it with diverse types of rocks and making some measurements directly in his bathroom. And after getting some exciting results, he decided to move to an application. And in 1927, he made the first electrical sounding in the Vosges Massif in the town of Pechelbronn. So you can see part of the apparatus here. There's a car and a lot of cables, and the results are measurements here with depths. And nowadays, field is looking like this, so you still need a lot of cables, and so you see several geophysicists on the field and we're actually working. But one of the biggest differences is that nowadays we have computers, and with the computers you can directly access information from the subsurface. So you see here a map of specific resistivity along a profile and varying with depth, and we will discuss how this data is basically acquired and processed during this lecture. So for the basics, the parameters that will be measured with geoelectrics are the electrical conductivity of the soil or the rocks. So typically it's written as sigma, it's measured in Siemens per meter, or the specific resistivity, which is labeled often as rho, and it's measured in ohm meter. There's a relationship between the resistivity and the conductivity. It's just the inverse relationship, so keep that in mind. So just for the basics, what's the electrical resistance? You all know what a resistance look like, but we need to make the link now with the subsurface. So a resistor in an electrical circuit looks like this, and here you would have a battery. So the plus and the minus here, the current is flowing from the plus to the minus, and it's passing through the resistor. And you can imagine the resistor as a pipe with a fluid flow going through it. If there is more resistance, then the flow is less efficient. So that's exactly what the resistor is doing and what the resistivity in the soil will do. It will limit the current, transfer of current. So one of the targets of geoelectrics is to measure the spatial variation of conductivity and resistivity inside the subsurface. So this can reveal important information about the structure of the substratum. So again, that's the picture of a profile along which a measurement is being taken and a final result showing you a measurement of the resistivity with depth and coordinate x along the profile. That's the target. And what is the mechanism for conduction of electricity in rocks and soil? Most often it's the presence of electrolytic fluids inside the pores of the rock, and sometimes it's simply the presence of metals inside the rocks. So what's an electrolytic fluid? It's basically, here you have an example of water, which is composed of a lot of stable water molecules, but sometimes some water molecules are dissociated into ions. So you have H plus and OH minus, and these these will be the electrolytes inside the fluid. Of course, in rocks and in the soil, you will have a lot of different electrolytes like sodium and so on. So these are different types of rocks. So you have sandstone, volcanic rocks, and fractured rocks, and all these types of rocks, they basically are characterized by a pore space. So there is some space, of course, between the grains in the sand. There are some space which is not fully filled inside sandstones. Of course, in volcanic rocks, you have the bubbles that make space, and in deformed rocks, you have fractures that make space. And within this space, the fluid can be located. And all of this rock texture will have an impact on the fluid distribution inside the rock, on the ore distribution inside the rock, and on the effective conductivity of the rocks in the subsurface. So for the basic properties of geomaterials, they can be measured in the lab, and that's basically a table that summarizes values of resistivity or conductivity for different types of rocks. And here you see in the blue square, these are the rocks which are the most frequently observed in the Earth crust. So you can notice the value of resistivity is from 1 to 10 to the power 4. So that's the range of values. It varies over many orders of magnitude. So from here to there, it's 10 orders of magnitude. And for the material, which is mostly observed in the crust, it's basically 4 orders of magnitude. So that's a very wide range of value. The last point, which is here the most important, is how to measure the resistivity ρ. And for this, we can use electrical currents and electrical fields. And this is to remind you Ohm's law. You have a relationship between the current, the electrical field, and the resistivity here. So if we know this and we know that, we can determine this parameter here in principle. So that's a sketch now of a 2-layer subsurface, hemispherical subsurface. So you see the surface is here. Below the ground, in the ground, we have 2 layers, one of high resistivity, one of low resistivity. And there is an apparatus which has been disposed here. 2 electrodes, A and B, are electrodes which are used to inject a current within the subsurface. A second set of electrodes, N and N, are used to measure the difference in voltage. These are used to measure what's called the potential or the electrical field. So what you see is how the current is being transferred through the ground from point A to point B. You see it's making arcs here. So that's the current line. And normal to the current line is the potential line. That's the electrical potential that is making circles. So that's very important figure that you will see a lot during the lecture. So now we have to go to basic relationships. So here is Ohm's law again. So we have U is equal to R times I. And we consider a cylindrical medium here. So this cylinder has a length of A and has a surface F. A current is injected and U is measured on both sides of the cylinder. So A is in length, so it's meter unit. F is an area, so it's square meters. The specific resistance can be expressed as R equal rho times A divided by F. So R has unit of ohm. What is the unit of rho? This you can simply work it out by solving this expression for rho. So rho is R times F divided by A. The unit of R is ohm, the unit of F is meter square, and the unit of A is meter. So this makes something in unit ohm times meters. So that's rho, the resistivity has unit ohm times meters. Now, let's consider one part of the apparatus. We consider one electrode that injects current. And we want to measure the difference of potential, V, between 2 points. So I is the point where the current is injected. It's going inside the ground. See, that's the air, that's the subsurface. And R is the radial distance from the point of injection. So R is this distance. dr is a little variation of the distance R. So U is a function of R. It's also the difference between two voltages. It can be expressed in this cylindrical coordinate. It can be expressed as minus I, the intensity, which is injected, times rho, the resistivity, divided by 2 pi r square, r being the radial distance, dr. So that's one expression. Then, if we want to solve for V, we can integrate the potential V along the radial distance. So let's integrate this to obtain V. So now we get an expression, V as a function of R is minus the integral from minus infinity to R of I rho divided by 2 pi r squared dr. And it's a trivial integral. It results in I times rho divided by 2 pi r. So that's a very important result here. This is basically showing you that V decreases as a function of 1 over r. So the distance r, the distance at which you measure the potential from the electrode, will greatly affect the magnitude of V. You can see on this diagram, this is a 1 over r decrease of a value. So if you measure V close to the point of injection, you will have a high value, and if you measure far away, you will measure very small values. So good measurements can be taken close to the current electrodes, but it's more difficult to get accurate measurements away from them. So keep that in mind. Another thing which can be noticed here is that if you solve this expression for the resistivity, then you get this 2 pi r V over I. And what you see here is that the relationship introduces a factor of unit meters, because r is a distance of unit meter and 2 pi has no unit. So let's consider a system which has 2 electrodes and 1 injection point. So we have A, M, and N. We have 2 distances. R, A, M is the distance between these 2 points. RAN is the distance between these 2 points. So we have this formula that we solved just before, and we want to measure the electrical tension for the set of 2 points M and N. So U will be V measured at point N minus V measured at point M. So we simply have to replace, to use this formula and substitute R by the actual distance between the injection point and the measurement electrode. So that's now more realistic equipment. You see a system in section view. You have 2 electrodes that inject current, A and B, and we have 2 electrodes that will record the potential field to measure the tension between the 2 points. So that's in fact a section view of the 3D figure I showed you before. So it's a little section here. So in practice, you will have a system with 2 measurement electrodes and 2 injection electrodes, and to measure tensions, now you need to involve a system with all these different points. So you need to know the radial distance between A and M, A and N, but also the distance between B and N, and B and M. And effectively, U can be computed using all these distances. A final expression, once again we solve for rho. An expression for the resistivity will be U divided by I times Kf. That's a very important factor. So this Kf, in the case of having all these electrodes, it can be expressed as this. It's simply by inverting this expression here, you will end up with 2 pi times this factor here. And this factor is the factor of unit meter we derived in the simpler case just before. So again, this shows you that if this is meter, then the specific, the resistivity here will be in unit ohm meters. So what's the effect of the subsurface? Because we obviously want to use this method to measure a subsurface which contains irregularities or inhomogeneities. So let's consider first a case where the subsurface is homogeneous. So you have 2 points here injecting current, and you see the current lines are going this way and the potential lines are making the circles around. So the potential lines are basically vertical here in the middle of the box. If now this layer here is made conductive, so it will be easier to conduct current, what happens now? You see that the current lines are deflected here and they are getting horizontal, and they are guided by the conductive layer here. In opposition, the potential lines are getting vertical inside the conducting body. So the whole picture here is being modified by the presence of an heterogeneity. Now if we consider another case, a poorly conductive layer, we will get the opposite pattern. The current lines, they will get locally vertical. So you see here, they want to become vertical locally behind the injection point. Here is the same. And the potential lines are getting locally horizontal. So you see the lines here just below the injection points. So there is a strong effect of subsurface structure. You can see the same here for the case of a vertical layer. So if the layer is conductive, you see that the current lines are being deflected down, and in the case of a conductive a poorly conductive layer, you have the opposite pattern. So now let's talk about resolution, because we can only make measurements at the surface, and the aim is to stay there and not to dig too many holes in the subsurface. So let's consider a system with two conductive anomalies. So these are the circles here, and you emit current from this point. So you see the current lines are being affected by the two conductive anomalies. The potential lines are also being affected by the presence of conductive anomalies. And if we have these two conductive anomalies a bit deeper in the ground, we will have a different type of perturbation. But what matters is what can be computed or what can be measured at the surface. So these are two measurements. One for the case, for the shallow case, is the red line. So when the two cylinders are close to the surface, you see a very strong amplitude signal. So you can detect easily that there are two bodies. But in the case these two bodies are buried too deeply, you only see a very wide bell-shaped profile, and you can barely distinguish the presence of two individual bodies. So the shallower structures are better resolved. It's difficult to resolve deeper structures. So that's for the conclusion of this first part. The geoelectrics can sense the subsurface. The resistivity of the subsurface is what is being measured. The resolution is limited, and we basically can find mostly shallow structures. And the subsurface structures, like layers and dikes, have a strong influence on the geoelectrical measurements.